Have you ever reached into your pocket and pulled out a handful of change and realized that it actually smells really bad, kind of like a musky, mushroomy type of smell? Well, there's a good reason for that, and it has to do with chemistry. And in fact, it's the same reason why we think that all metals smell. And it has to do with the chemistry of the metals and your skin oil. So in fact, metals do not have a smell. It's an illusion that we have created inside of our minds. So if you think about it, in order for something to smell, it needs to put molecules into the air. And so by that, it means it needs to evaporate. And metals do not evaporate. So if metals evaporated, I should be able to put a iron nail out and come back a certain amount of time later, and that metal nail or that iron nail should be gone because it evaporated. So metals do not evaporate. So the metal itself does not put atoms or molecules into the air. So the fact that we think metals smell comes from somewhere else. That smell comes from somewhere else. And in fact, we associate that smell with the metals themselves. So where they come from is the interaction between our skin oil and the metal itself. And what happens is this metal causes the molecules inside of our skin oil to turn into smaller molecules, and those smaller molecules are actually volatile, which means that they evaporate, which is what we need for something to smell. So the volatile molecules go into the air. So remember, whenever you smell something, whenever you get that sense of smell, really what your nose is detecting is molecules in the air. And who knows where they come from, but that's the idea. So we are smelling something, but we are not smelling the metal itself. What we are smelling is the decomposition of our skin oil. So literally, metals smell because of skin oil that's been put on them. So there's a chemical reaction that actually occurs. So the skin oil itself doesn't smell. It's a large molecule. It's not that volatile. So we need to decompose the skin oil and turn it into smaller molecules. So what happens in the first place is when we touch something, so we're going to use iron as an example, the perspiration inside of our skin corrodes the iron and produces Fe2 plus ions. And you might have seen this if you have a highly polished blade like a knife or a sword. If you touch it with your thumb, you can come back and literally see your thumb etched in rust on there, because our skin oil causes iron to corrode. And that's why people are very sensitive about touching metals, and why you need to clean metals and keep them oiled, because they will corrode if you do not take care of them. So inside of your skin oils, there's multiple different molecules. So we're looking at one here. So they're oils. So we've seen this. This is kind of a generic skin oil molecule. And the oils, along with Fe2 plus that we made from the corrosion of our metal, iron, react with air, and it causes this molecule to break down. So the skin oil molecule is rather large, so it's not that volatile. And I'm not going to talk about the mechanism of the reaction, but after this reaction occurs, the skin oil molecule actually decomposes to form smaller, more volatile molecules. And so this is actually the main one. It's called 1-octene-3-one, and it makes up about 1/3 of the odor that we get from metals. And the idea is, if you were to smell a bottle of this molecule, you would say you would describe it as being metal or mushroom-like, or having a mushroom-like smell or a metallic smell. And this is the idea. This molecule doesn't smell like metals. This molecule smells like itself. And because this molecule comes from metals, we associate the smell of this molecule with metals. So once again, it's an illusion. The metals do not put off a smell. The metals cause a skin oil decomposition that produces this molecule, plus a bunch of other ones. And it's this molecule that makes us think that metals have an actual smell. So why do some metals smell and other ones do not? So this gets into the actual chemistry. So the iron decomposes, so that means it loses 2 electrons to become Fe2 plus. And if you go through, and especially if you've learned electrochemistry, every metal has a different ability to give up 2 electrons to become a cation in this case. So every metal has a different ability to corrode when it comes in contact with skin oil. So if you look at this, some metals want to give up electrons, some metals do not. And the ones that want to give up electrons are the ones that corrode and the ones that smell. The ones that do not give up electrons are the ones that do not smell. So in particular, copper and brass and iron give up electrons easily, and they tend to produce this odor. So in particular, copper tends to have a very, very sharp kind of smell to it. But if you look, gold, magnesium, nickel, and aluminum do not smell at all. That's because they do not want to lose electrons and go into their cationic form. So a gold watch doesn't smell bad. Aluminum can does not smell bad. So another place where this idea comes up, where our skin oil decomposes, is whenever we get a cut or we get blood on our skin. And what happens is the blood actually has iron inside of it. So iron is inside of our blood in the form of hemoglobin. So hemoglobin has Fe2+, and remember, it's Fe2+ is the form of iron that we need to cause this decomposition of skin oil. So it's almost like blood has pre-decomposed our skin oil. So what happens is the blood comes in contact with our skin oil, and there's oxygen in the air, and the skin oil decomposes. So just the same way our skin oil decomposes when it touches a metal, our skin oil decomposes when it comes in contact with blood. And so that's why many people think that when they smell blood, they think it smells like a metal. So the same deal, we're not smelling the blood so much as we're smelling decomposed skin oil. So one thing that's really, really interesting is this main molecule that produces the smell for metals, the 1-octene 3-one, is very sensitive to our noses. So this is one of the more sensitive smells to our nose, and we can actually detect, so this is human beings can detect them in a parts per billion level. So our nose smells this quite a bit, and it makes sense. When you have skin oil and you're reacting we're only producing a very, very small amount of this smell. And it's one of the things, if you think about it, you always wonder what it would be like to have a nose as sensitive as the dog's. Well, for this one molecule, our noses, human noses, are as sensitive as a dog. So dogs can perceive smells down to the parts per billion. Well, we can perceive this molecule down to the parts per billion. And if you ever want to prove this, try to get the smell off of a handful of change, and it's almost impossible. So you can wash it, you can do whatever you want to it, but even if there is a very, very small amount of this molecule left on the change, you will still smell it. So there's a theory on why is our noses so sensitive to this particular molecule, and there's numerous theories, but one of the ones says that this gave our ancestors the ability to track prey better. So if we can wound an animal, the animal is going to bleed, and then the bleeding is going to cause the production of this scent molecule. And if we are very sensitive to this scent molecule, we can track the prey a little bit better. So that's one of the theories on why our nose are so sensitive to the smells of this decomposed skin oil based molecule. So with that, this is the end, and hopefully you can subscribe to the video textbook of chemistry.